Hi everyone, and welcome back to Spaced Out. So today is a really exciting episode for me because I'm going to be interviewing one of my favorite professors at Caltech, and actually my very first astronomy professor, Professor Mansi Kasliwal. So today we're going to be discussing and breaking down her research and the types of topics in astronomy that fascinate her. I'm really excited for this episode and to break down your research a little bit. It would be great if you could start by introducing yourself a little and talking a little bit about your journey and how you ended up here at Caltech.
Sure. So my name is Mansi Kasliwal. I'm a professor of astronomy here at Caltech. I joined the Caltech faculty about 10 years ago now, in 2015. Before that, I was doing a fellowship at NASA Hubble Fellowship at Carnegie Observatories and Princeton University. Before that, I was at Caltech, actually, doing my master's and PhD. And even before that, I was at Cornell. And before that, I was at Bryn Mawr College. And and I grew up in India, in a place called Indore in India. And went to the same school from kindergarten to 10th grade.
Cool. Well, we can start talking a little bit about your work and what you do. So a lot of your work focuses on what you describe as cosmic fireworks. Could you explain to us a little bit about what you mean by that and their significance?
Sure. So when I love discovering new types of cosmic fireworks, and what these are flashes of light. Yeah. So just like a firework is a bright flash of light that only lasts for a few moments but is beautiful and has many different colors and many different types and many different properties. Cosmic fireworks are when one star or two stars at most interact in a manner where they could become 1 million to 1 billion times as bright as our sun. So they're normal stars that are either merging or they're the dead remnants of normal stars like white dwarfs, neutron stars, or black holes. When they merge, interact, explode in different ways, you get these really luminous flashes of light, which are many, many orders of magnitude brighter than our sun. But they're fleeting moments. They could last for seconds, they could last for hours, days. But they're much, much shorter periods of time compared to the lifetime of a star, which would be millions to billions of years.
And why are they so significant for us to observe, other than that they're so cool to see?
So they're very significant fundamentally because in these fleeting moments is where most of the elements that you and I know around us are actually synthesized. So most of the universe is actually quite simple, right? It's just hydrogen and helium, and that was formed in Big Bang nucleosynthesis. Everything else, right? I mean, if you look at the next several rows of the periodic table and many of the elements that you and I are made up of that we use every day in the world we live in, these elements are not made easily, right? And they're made in these very luminous, very bright explosions. So they're wonderful laboratories or mines, so to speak, to make and create elements.
Yeah, that's a great way of describing it. We often hear, or at least how I've learned about it, is that stars can fuse different elements depending on their mass. And so how do we know, what stars fuse what elements? And what have we discovered so far about the stars themselves?
Yes, so let's start with the sun. So the sun is going to fuse hydrogen into helium for 10 billion years of its life and then become a white dwarf. Stars a little bit more massive than our sun will go a little bit further, right? They get a little bit hotter in their core, and they can not only fuse hydrogen into helium, but helium into carbon, nitrogen, oxygen, that into silicon, sulfur, all the way up to iron. But then that's it, right? I mean, when you reach iron, the star runs out of... it's no longer efficient to fuse into heavier elements. So an iron is not even halfway through the periodic table, right? I mean, there are many, many elements in the periodic table heavier than iron. So the cores of stars can get us through select elements up to iron, but not everything, even up to iron, and certainly nothing heavier than iron. So for that, we need supernovae or kilonovae or some of these cosmic fireworks to make those heavier elements.
Okay. And do we discover that the stars have fused up until iron from the supernovae? Once they explode, we can see those traces of elements, and that's how we know?
Yeah, so that's a great question. So when supernovae of type 1, right? I mean, when type 1a supernovae happen, these are explosions of white dwarfs.
Yeah.
And so when they explode, then you synthesize about 2/3 of the iron group elements. So 2/3 of the iron in our blood, right, is made in type 1a supernovae. Because that is when a lot of a carbon oxygen white dwarf is getting is exploding, so you can actually go through the thermonuclear cycle very efficiently and burn an entire solar mass worth of carbon and oxygen all the way to iron and produce a lot of iron group elements. Nothing much heavier than that, but the iron group elements are all synthesized or mostly synthesized in type 1e supernovae.
Cool. But as you mentioned, even with stellar fusion and these supernovae and kilonovae, or we haven't really spoken about kilonovae yet, but we're missing the origin story for so many of these elements, right?
Right.
But there's a major event in 2017 that you were a big part of that helped change that. So maybe you can tell us about the observation and how important it was.
Sure. So on August 17th, 2017, I remember the date exactly, right? It was definitely a defining moment, a watershed moment in my life. For the very first time, we as in humanity saw the merge of two neutron stars and saw a black hole being born, right? I mean, and this was spectacular because we saw the longest, loudest gravitational wave signal ever. And we saw the entire electromagnetic spectrum light up. And to me, the most fascinating piece of this was actually the infrared, because what we saw very vivid, very direct evidence of for the very first time is the synthesis of half the elements in the periodic table heavier than iron. So this is what is called R process nucleosynthesis, where the R in the process stands for rapid capture of free neutrons. So you can imagine when you're trying to make heavier and heavier nuclei, the biggest challenge is how do you stuff all those neutrons and protons into a nucleus without them repelling each other and wanting to stay unbound, right? So you have to do this very quickly, and you have to do this in an extreme environment where you have lots of free neutrons. Right? Because if you just take a neutron and you put it on the desk here, in 10 minutes it will decay. It'll beta decay.
Yeah.
So it will not want to go and live with so many other neutrons packed in a nucleus, right?
Yeah.
So in order to overcome that physics, you need to very rapidly capture these neutrons in very extreme conditions. And when a black hole is being born, if it's right after two neutron stars are merging, then you have an abundant supply of free neutrons and conditions extreme enough that you can actually make nuclei heavy enough to explain, the elements in the periodic table heavier than iron.
Wow.
So this is everything from silver to gold to platinum, right? Those are the ones that people most easily recognize, but probably gobs of neodymium, based on how when you model the spectra, which elements dominate the production.
Yeah. So a lot of your work then involves observing in the infrared, right? And why is it so important? The infrared, why is that so important when it comes to studying these fireworks? That's
another excellent question, right? So the infrared is really valuable because when we are trying to see the synthesis of these very heavy elements, what we are looking for is radioactive decay, right? So we are looking for radioactive decay of these elements, and then when we try to get those photons from millions of light years away to our telescopes, right? So when these photons are trying to make their way to us, the problem becomes that when a heavy element is made, it's very easy for that photon to get distracted. So that photon can very easily, because in a heavy element you have so many possible line transitions, right? You're filling electrons not only in the S shell, but the P shell, the D shell, the F shell. So there are many possibilities of where a photon can get absorbed and bump an electron. And another, there are millions of possibilities literally for that photon that's trying to come to our telescope to get instead absorbed by an electron along the way. So what we refer to this in technical terms is that the opacity is really high. Right? So the opacity is 10 centimeters square per gram. What this means is the bulk of the emission, instead of being bright in the optical bands, is shifted into the cooler, longer wavelength infrared bands. So the bulk of the emission from these heavy elements is in the infrared because of fundamental nucleophysics.
Yeah. So if we look in the optical, we just wouldn't be able to see as much as we do.
Exactly. So it's purely atomic physics that forces us to look in the infrared. And the infrared is a tough place to be, right? I mean, the night sky is much brighter in the infrared. Making detectors is much more expensive in the infrared.
Yeah.
So, but the astrophysics, if you want to go and study these heavy elements, in particular the heaviest of the heavy elements, infrared is where you need to sharpen your toolkit.
And can you help us understand like the sheer scale of these objects? You've mentioned like white dwarfs and neutron stars, but I think for a lot of people, even for me, it's hard for me to understand how dense these are, that they're able to fuse such.
Yeah, and that's a great question, right? So, so we all know and understand, okay, it's something like the sun, right?
Yeah.
I mean, the sun is about a solar mass and about a solar radius. You know, astronomers always refer to the sun as unit 1, right? So now think about taking the whole sun, right? This beautiful bright star next door, and packing it into the radius of the Earth, right?
Wow.
So if you pack a sun into Earth, you'll get a white dwarf.
Yeah.
Now, if you take the sun and instead of packing it into the radius of the Earth, you pack it into the city of Pasadena, right? 11 kilometers in radius. That is what a neutron star is.
Wow.
So if you try to take a teaspoon of any of these things, it'll be tens of thousands of metric tons, right? So you cannot hold a teaspoon of a white dwarf or a neutron star. So in terms of density, you know, a white dwarf is something like 1 million grams per centimeter cube. So 1 centimeter by 1 centimeter by 1 centimeter is 1 million grams. And neutron stars are 10 to the 15 grams per centimeter cube. So it's unimaginable. It's even hard to imagine,
so true.
You know, that how do you get 10 to the 15 grams in 1 centimeter cube.
Wow. And are there still any elements whose origins we're waiting to discover? Like we're waiting for other events to explain them?
Absolutely. So I would say, you know, when we saw these two neutron stars merge, we knew that elements heavier than iron were made.
Yeah.
But what we had definitive proof for was even amongst the heavy elements, we had definitive proof for, say, the 4th row of the periodic table. We didn't have definitive proof of you know, the lanthanides and the actinides in the periodic table.
Okay.
So the heaviest of the heavy elements, it's still very debated whether or not we saw it in this completely you know, watershed moment and epic event. And we have some clues that suggest that, you know, the synthesis went all the way through, but the bulk of what was made was the next few rows of the periodic table, not that very last actinide row.
Yeah.
So we saw 2 data points from the Spitzer Space Telescope back then, which was sensitive to the reddest emission at very late time. And it was all of 2 data points, right? And that was just imaging points. We didn't have at that point the James Webb Space Telescope. With its exquisite sensitivity to study this late-time emission and tell for sure whether or not the heaviest of the heavy elements were made. So I couldn't tell you whether or not gold or platinum was actually synthesized, right?
Right.
I could tell you that, you know, silver for sure. We made plenty of that. But I think that it's an open question whether another neutron star merger with the James Webb Space Telescope, if we go and look, whether we'll see the heaviest of the heavy elements, or they're made elsewhere, or they're made not when 2 neutron stars merge, but say a neutron star merges with a black hole. So because if you have a neutron star merging with a black hole, that black hole is capable of tidally pulling out a lot more material from that neutron star than another neutron star. So you have even more abundance of free neutrons and an even more extreme cosmic laboratory to make the heaviest of the heavy elements. But so far, we've never seen light from a neutron star black hole merger. We know they're real because in 2019, we saw gravitational waves from them. So they're no longer a theoretical construct, right? So we've seen neutron stars get merged by other black holes or get completely engulfed by other black holes. But we've not yet seen the light from them. So we've not yet seen photons emerge from this sort of cosmic event, and so that we can study what elements are made, if any. Because there's a possibility that the black hole just swallows the neutron star whole, and so there's no time to make any elements and disperse them in the interstellar medium. Or there's a possibility that there's so much stuff around that black hole that you actually make the heaviest of the heavy elements in very large quantities and then distribute that to the surrounding interstellar medium. So that, I would say, is an open question. And
That's interesting.
Anytime there's a neutron star black hole merger, the telescopes drop what they're doing and will go and try to look for the light. So if there's no light, it probably means that the neutron star got swallowed whole by the black hole.
Oh, but we haven't seen the other case.
Right. So if the black hole is much heavier than the neutron star, say the black hole is 10 times more massive than the neutron star, then chances are it's going to get swallowed whole.
Right.
But you have small black holes and you have big black holes, right? So if there's a neutron star black hole merger where the black hole is only about maybe 2 solar masses or 3 solar masses, and the neutron star is 1 solar mass, in that case, you could have this perfect balance where the black hole is not so massive that it's going to swallow the neutron star whole, but the black hole is still more effective than another neutron star at ripping out that free neutron material. So we expect to see light from neutron star black hole mergers, theoretically, right? But I only believe it when I see it. So we have to wait to see it.
Right. Have we seen any or evidence of any black hole mergers, or would that be a case where we don't see light at all?
So we've seen now more than 100 black hole mergers, and a handful of them, in fact the heaviest black hole mergers, there seems to be some tantalizing evidence that they're associated with some sort of flaring activity around a neighboring supermassive black hole. So not only are there the two, like say 100 solar mass black holes that are merging with each other, but these two are next to a third billion solar mass black hole. And because there's so much going on in that surrounding, right? I mean, there's a lot of gas and dust and activity, that when that 100 solar mass black hole merge, it sets off some small flare. Not really nucleosynthesis, not really the synthesis of elements, but you see some photons, some light from a handful of black hole mergers. But it's very debated whether that is, really, it's not as direct and vivid and slam dunk evidence as with the two neutron stars merging. So it's debated in the literature whether or not we've seen light from black hole mergers.
And are you working on anything similar right now, like connected to this research, or do you think you've strayed a little bit from the 2017 event? I work on many things right now, but I still love this question. So what I'm trying to do is I'm very interested in this neutron star black hole question. So what I'm trying to do is, I think one of the reasons we may not have seen a neutron star merge with a black hole is because we don't have as sensitive a pair of infrared eyes as we need. So I'm trying to build a new infrared telescope in Antarctica, which is called cryoscope. So it's not even a telescope because it's so cold that we call the whole thing a cryoscope. But it will be very, very sensitive in the infrared. So it will be capable of seeing light from these neutron star black hole mergers all the way out to 400 megaparsec, which is 1200 million light years away. So if there is light to be, if these heaviest of the heavy elements are being made in neutron star black hole mergers, I'm determined to go and find that. Awesome. So sharpening my tools so that if it's a telescopes are not sensitive enough, and maybe these things are just dead in the optical and they're only bright in the infrared, right? As you would expect from atomic physics. And if that's the case, then we need more sensitive infrared telescopes. And exactly. So the sky is very bright where we live, right? In the temperate locations, the night sky is very bright in the infrared. If we go to Antarctica, well, it's a nice cold place. That's fun, but and the penguins are cute. But but the bigger advantage is that there is a bandpass in the infrared, a window in the infrared where the night sky is 40 times darker. Oh, wow.
So if the sky is darker, that means with the same size telescope, you can see much further. It's just much, much more sensitive. So that's why I want to try to build this telescope in the Antarctic.
How far have you gotten on that?
Right now, I'm testing some new technologies.
That's awesome.
And so we have a little pathfinder, which is about a fifth scale of the whole system.
Yeah.
And I have a student whose PhD thesis this is.
Cool.
And it looks good in the lab. It seems like it's working in the lab. So now we want to try to take this pathfinder to the Antarctic and test it on Sky there. And if it works there, then we'll be ready to build the whole thing.
So you're going to the Antarctic to test it?
Yeah, hopefully next year.
That's so cool.
Hopefully next year. Yeah.
That is awesome. Well, thank you. That's all I wanted to talk about today, but I learned so much, and I hope everyone listening, probably they'll learn a lot too.
My pleasure. Always really fun to talk to you.
Thank you.